Hi, Robin here. This is Logistic Regression 5. It's a practical supplement to Michael Campbell's excellent little book, Statistics Squared 2, Chapter 3. We'll look at how to do some of the analysis he describes and some additional ones in SPSS and R. As you know, logistic regression is where we have one or more input variables of any type, really, and then one binary outcome variable. We'll be looking at a particular type of logistic regression, this time called conditional logistic regression. Conditional logistic regression. In conditional logistic regression, it allows us to analyze matched or paired data, and you get that situation where you have a case control style analysis where you have controlled and cases. We'll be looking at some examples in a minute. Another type of trial is where we have follow-up studies, where we have exposed or unexposed individuals and we want to compare them. And the interesting thing is that this relates to the outcome variable. So conditional logistic regression refers to the outcome, which is disease or status. And this is basically a logical extension to Mac-Nemer's test, which I've talked about before, and it takes into account, as I say, possible confounding effects of one or more variables upon this matched or paired outcome variable. Campbell's little book doesn't really describe much about this type of regression, and actually there isn't much about it anywhere if you look. One excellent source is this, Kleinburn and Klein, Logistic Regression, a self-learning text, and its third edition's just come out, I think. Right, so let's look at an example. Michael Campbell gives an example here of the inadequacy of monitoring and hospital deaths and survivors among 35 matched pairs of asthma patients. So we have 35 pairs of patients, and 35 of them were people that died in hospital from asthma, and the other 35 were what's called historical controls, those that didn't die. And he wants to compare between the two groups the adequacy of the monitoring, whether it affected the outcome. So we have a control group we could call are those that have survived, this historical control group. Then he matched them for age and various other things to those that died from asthma. You want to see if there's a difference between the inadequate and adequate monitoring proportions. So it's just like Mac-Nemer here because we've only got one variable. So we consider though the ones that in adequate monitoring and adequate monitoring to the cases and the controls. And similarly we look at the difference between the inadequate monitoring and the adequate monitoring for those that controls and cases. So we only look at where things change, not where things are concordant. How do you enter this data into SPSS? Well, here we are. We have 4 columns. This thing called strata I've introduced here, and you'll see why as we work through this tutorial. Strata is basically the pairing. This would go on for 35 pairs, so 2 1s, 2 2s, 2 3s, up to 35 times 2. Then the outcome, which is 0 equals survive, 1 equals they were dead. And monitoring, whether it was adequate or inadequate. And then the case control is actually equivalent, if you think about it, to the outcome, because we have a one-to-one correspondence here. We might not necessarily have this. We might have more than one control. So we might have one case, 2 controls, one case, 2 controls. And there's our equation. Very simple this time. So the important thing to notice is that a dependent variable is dead alive, which defines the case and control groups. So all those in the control group were alive and all those in the case group were dead. But we're considering them equivalent by matching them on various covariates like age and possibly other things. So to carry out the analysis, we actually need to trick the software, and that's a similar situation in both SPSS and R. In both situations we use a thing called Cox regression, which we talked about in survival analysis YouTube videos, and what we do is add a grouping variable, time. So how we do this is all the cases had the event at the same time and all the controls were censored at the same time. This is just a fake really variable. dummy variable, it's necessary so we can actually run the analysis. So we say all the cases had an event and all the controls were censored. 1 equals case, 2 equals control. So we would class 1 as the event when we're analysing the data. And we can get results like this. So an odds ratio of dying with inadequate monitoring was 4.33. So that means there were 4 times the odds of dying with inadequate monitoring. So those that had inadequate monitoring had 4 times the odds of dying compared to those that received adequate monitoring. But that's not really demonstrating conditional logistic regression. The nice thing about conditional logistic regression is that we can add additional predictor variables. So here I've added BMI to that dataset, body mass index. They didn't pair the data on body mass index, so that's, I'm pretending that we actually got this data from the cohort as well. And notice that that is interval ratio data and it's not matched, as I said. Each interval just supplied the value. And we have, as I say, the case control variable. And notice it's case control, 1 case, 1 control, 1 case, 1 control. It doesn't have to be, it can be 1 case to several controls doing it. So here we are, here's the equation now. We've added an extra predictor variable, BMI. Again, the dependent variable is which kind of group they belong to. Right, let's look at another example. This example isn't given in Campbell, but I've given it here because it provides a bit more detail about this technique. So, what we're saying here is the role of induced and spontaneous abortions in etiology as secondary sterility was investigated. Obstetric and gynecological histories were obtained for 100 men with secondary sterility. Women with secondary sterility. For every patient, an attempt was made to find 2 healthy control subjects from the same hospital, matching for age, parity, and level of education. And they did this for 83 index patients, that is 83 patients. So here we are, this is how we'd enter the data described above. So we have the case number on the first left, then education level, then age, parity, whether it induced abortions, and the status, whether it's controlled or a case, and then spontaneous abortions for that particular case or control, and then we've got stratum again, which is basically the grouping. So we have 3 observations in each group. We have 1 case and 2 controls. And I've added this additional variable which is necessary to get the data working in R and SPSS, which I'll talk about again. So here we are, here's the equation this time with some additional independent predictors. And again, that the outcome variable, the dependent variable, is case control group values, which is whether they're sterile or healthy. And I've taken this example from the R survival package, which contains several datasets. One of the dataset is called the Inferred dataset, and it's taken from an article in 1976 in the British Journal of Obstetrics and Gynecology. It was actually analysed using a different technique because conditional logistic regression wasn't really available in the 1970s. So here is our first example concerning adequacy of care and survival in asthma patients. Just to check that we have the coding, we have 1 that equals death in our outcome variable, and then case control, 2 equals control, 1 equals case. Right, to carry out the analysis, we go to Analyze, Survival, Cox regression. We type in here in the time variable, case control, which is a fake value really, and then outcome, we define our event, we define death as being the event, and those that survive are censored, and then covariates, let's just do the monitoring covariate first, and for the strata, this is why I call it strata in one of the examples, because strata is actually pairing, so it might not just have pairs, it might be 3 or 4. Remember in the other example you had 1 case to 2 controls. So options we go to, and we want the confidence interval for our estimate. Continue, OK, and here are our results. And we can ignore most of this output. All we wanted was our odds ratio. If we look down here, there we are. Exponentiated beta is 4.33, and there's a confidence interval. The beta is actually the same as Campbell's. Confidence interval is slightly different. Campbell discusses why this is the case in the text. Right, I can repeat the analysis now, putting in the second covariate, which was the BMI. OK, and here is the results this time. Notice this time that adding BMI as a predictor is totally insignificant. Makes no difference whatsoever, and disregard it. Here is our data set for the acquired infertility example that I talked about before, with a case number, educational level, age, how many kids the person had, whether they had had a spontaneous abortion or a induced abortion, and status, which if we click on here we can see what it is. One case, two controls, one case, two controls, which is different from our previous example, and the stratum, which groups those three observations together, and then this fake variable, fake time, which we need for the Cox regression, so we can get a odds ratio estimate. So to achieve our analysis, we just go to Analyze, Survival, Cox regression. Analyze, Survival, Cox regression. Time, we put in our fake time variable. Status, we put in the status variable, I called it, there we are. And we're going to give the value 1 to the event, which is the actual case rather than the control. And then covariates, we're going to put in whether they suffered a spontaneous abortion or an induced abortion. And the strata, well, I called it stratum there, which is the group of three observations. Remember, the one case and two controls. Options, we just want to ask for a 95% confidence interval, continue, and click OK. Ignore most of the output, go down to the bottom, which are the things we need, and there are our parameter estimates and odds ratios for the spontaneous abortion and induced abortion. Notice both of them are highly significant, and that has an odds ratio of 7.2 for spontaneous abortion, and induced abortion has an odds ratio of 4. Be interesting if you go and look at the original article, it used a simpler method of analysis and see how the results compare. One thing I should have mentioned was how I actually added that new variable to the data set. If we just look quickly here, you'll notice that f time. And f time is equal to 1 or 2. 1 or 2. 1 when we have a case, and 2 when we have a control. And that wouldn't have been the original data set. We've added that just for the purpose of actually being able to carry out the analysis using a Cox regression to get our odds ratios. Let's do this very easily. You just go to Transform, Compute Variable. And when I put in my new variable name there, target variable, and I said target variable is equal to 1 plus 1 if the status was equal to 0. Otherwise it kept it the same. So if you notice here, we have for the case when status is 1, that equals 1, and status is 0, that equals 2, and that's what that little expression does. It updates that, and you just press OK, and it will press OK, and it will compute that new variable with those values. On to how to carry out the analysis now in R. Hi, we're going to be now using R Commander and R. So first of all, we've got to load R Commander. Once we have R Commander open, then we use data, import data, SPSS. We don't want factor levels, and we'll call it my data. Okay. Find the file, check to see if we've imported the right data. There we are, yes. pairing, outcome, monitoring, case control, and BMI. And back in here, we need to attach my data, which we just called it. We type my data. We see the data now. There. And it's actually only one command to carry out the analysis. And here is the command. Model equals clogit, clogit, C-L-O-G-I-T, which stands for conditional logistic regression. Then dependent variables outcome tilde monitoring plus BMI, and then we have to specify the pairing, which I've actually called it pairing. Shall I get the names? There we are. So we can see there it's the strata, exactly the same as we had in SPSS, obviously. Press return. Don't see anything until we type summary command. And there we are. You notice monitoring 4.37, BMI 0.979, probability values there for monitoring 0.02, and BMI completely insignificant 0.82, identical to what we had before, and the confidence intervals are given as well. Now we're going to carry out the next example. As I said, the other example, the dataset's actually within R in the survival package, and it's called Inferred. So all we need to do is say attach Inferred, and we have that data. If we just type Inferred, we'll see it. There we are. Education, age, parity, induced case, spontaneous, stratum, and we can ignore the last one. Notice that when I used the SPSS version of that file in the SPSS example, actually I changed the name slightly because SPS doesn't like long field names. So we just use a similar command as we did just now. So we have here, I've called this model 2, clogit case tilde spontaneous plus induced plus the strata. This time I just put in here that data is inferred. We actually don't need that, but sometimes you put it in to make it a little neater. Press return. Can't see anything to type the summary command. And there are our results. And if we check back, you'll see they're identical to what we had before. We've carried out an awful lot in a very short time there. We first of all carried out logistic conditional logistic regression in SPSS by using the Cox regression command, and to enable us to do that we had to create a fake variable which allowed us to put something in the time box so we could do that, and we used the compute variable command to achieve that. And if you look at the above, f time was equal to 1 if it was a case and 2 if it's control, and we based those values on the status variable. We also had to use the status field in the actual status variable in the Cox regression box, and in that instance case had to equal 1 and control equals 0, and the stratum here in the Cox regression box was just the variable that described the pairings. Then we came to R and we used two datasets there again. First dataset we imported using R Commander, and that was from an SPSS data file. Then we used this command called clogit. It looks very much like the LM or GLM commands we've used in the past, except we've got this new little bit added called strata pairing. And the strata again, as it is in SPSS, is the pairing variable. The second dataset we used, the infertile one, was actually within R itself, and that was in the survival package, which contains some other datasets that are very useful for this type of analysis. And we used the C logic function again. I added an extra little bit on the end of this command, data equals inferred. We didn't really need to do that because we'd actually put the attach command inferred before, so it knew which data set we were using. There are some excellent books around concerning logistic regression, and if you are planning to carry out logistic regression for your dissertation, I suggest you get hold of this book by Klein, Byrne and Klein. It's an excellent self-learning text with lots of exercises, lots of multiple choice questions and what have you. Problem is it's very expensive, so get it out of the library. The other book, of course, I recommend is Statistics at Square 2, where I got most of these examples from and the explanations. Michael Campbell's book is excellent, and actually, although it's only covered about 10 pages, it talks a lot more about using logistic regression in various other situations, such as meta-analysis. Definitely recommend you read that chapter very carefully.